Okay, the first question is consider the definition given below. It reads the high energy transition state between products and reactants. So this is the definition of A. We've got the option of a catalyst, then B, heat of reaction, and then C, activation energy, and D, activated complex. So if we are to look at option A, they are saying a catalyst. So a catalyst, we know it's a substance that actually speeds the rate of reaction without being used up, right? So according to this, option A is out. Then heat of reaction, we know is the difference between energy of the reactants and the energy of the what of the products. So this one is not the one again. So A is out and B is out. Then C says activation energy, which is the minimum energy required to start a chemical reaction, is also out. So now the unstable transition between products and reactants is activated what? A complex, which is defined as the high energy transition state between products and reactants. Then we move on to question 2, which reads which one of the following ions can act as an ampholyte? So we're looking for an ion which can act as an ampholyte. So now the first option that we're actually having is HCO3 in negative, right? Okay. So if we can define an ampholyte, what is an ampholyte? An ampholyte is a substance that can either act as a what? As a base or an acid. So in this case, the one that can actually act as a base or an acid is actually going to be option A, which is our HCO3 negative, right? Then 1.3, it says consider the interatomic bonds shown below, right? So we've got a carbon-hydrogen bond and a carbon-oxygen bond, right? It says which one of the following combination regarding the bond length and the polarity of the bonds is correct? So which one of the following combination regarding the bond length? So number one, we're focusing on the bond length, and then the polarity of the bonds is actually correct. So according to the information here, we know the shortest bond length between carbon and hydrogen is always short. This one, so the shortest bond length is actually going to be between carbon and hydrogen. Then here, after these options, it means option B and C, they are already out. Option B and C, because they are actually going to have a longer bond length compared to carbon and hydrogen, right? So now we're looking at the polarity of this, right? So the one that is actually going to be the most polar here is carbon and oxygen. So carbon and oxygen has got a higher polarity compared to the one that has got a CH bond. So the correct answer here is going to be our letter A. So letter A is the correct answer for 1.3. Then as we proceed, we're looking to add the conjugate base of the ion, which is H2PO for negative E. So base pairs, remember these acid base pairs this here, the conjugate base. So we're looking for the base of the ion H2PO4 is. So according to the information that we're given here, this H2PO4 acts as what? As an acid. So now what we're looking for is the one that is actually going to be a base. So if we were to say H2PO4 negative, and then on the other end, we need something according to this equation, the one that says PO4 3 negative is actually going to be wrong, because here what we are looking for, remember, when it comes to acids and bases, we define them according to Arrhenius here, which is saying an acid is a proton donor and a base is a proton acceptor. So the one that can actually act as a proton donor here is actually going to be our option C, which is your HPO4 negative, 2 negative there. So the correct answer there is going to be HPO4 2 negative. Then we move on to question 1.5, which reads the table below shows the melting points of water. So melting point of water and hydrogen bromide, your HBr there. Then compounds H2O, then HBr. Then the melting point is in kelvins, 273 and 159. So it says which combination below correctly lists the strongest intermolecular forces? Which combination below correctly lists the strongest intermolecular forces? So we're looking for the strongest intermolecular force in H2O and HBr. That explains the relatively high melting points of these compounds. So option number one, we're having option number one, which says in H2O there are hydrogen bonds. So it says in H2O there are hydrogen bonds. Then the second option reads in HBr there are London forces, right? So if you look at H2O, does it has hydrogen bond? So H2O, so if you look at H2O and then HBr as a comparison, that explains the relatively high melting point. So we're looking at the melting point of these compounds. So the main thing that we need here is the melting point of these compounds, right? So option A says hydrogen bonds. In H2O, there are hydrogen bonds. Then yes, H2O has actually hydrogen bonds. That's correct. Then in HBr, it says they are London forces. London forces there. Then the second option, remember, when it comes to hydrogen bonds, what we actually need is F, F-O-N, F-O-N. So when these are actually bonded with hydrogen, that's when we actually have what we can refer to as what? Hydrogen bonds. So here, in terms of this one, option C and D, they are the odd ones out automatically because here, these ones, H2O, dipole forces and London forces, we do not count them when it comes to H2O. Then here, the option B says hydrogen bonds and dipole forces. So in London, in HBr, we have what we refer to as dipole bonds. So the correct answer here is actually going to be letter B. Then we move on to 1.6. Says a pair of electrons that is shared between two atoms in a covalent bond is called a. So if you are sharing that pair, it means it formulates a bond with the other, with the two. So a pair is a two. So at the end of the day, a pair of electrons shared between two atoms in a covalent bond, they are referred to as the bonding pair. They are the bonding pair. Remember the lone pair as the one that, like, for example, if we're having our oxygen, if we're having our oxygen from the periodic table, if you can check the periodic table, it means oxygen has got how many electrons on the outer shell? Oxygen has got is it 8 electrons on the outer shell? So on the outer shell, 6 electrons. So it's going to be 1, 2, 3, 4, 5, 6, right? So these are referred to as the lone pairs, right? So these other two are the ones that are actually going to be involved when it comes to bonding. So these are the ones that are referred to now as the bonding pair. Then the lone pair are the only ones that are already paired within that that element. Then the bond length is out, and then the valence of electrons, remember valence of electrons, those electrons that are actually found on the on the outer shell. So with having said that, the correct answer is going to be the bonding pair. Then we move on to question number 1.7, which reads an air in a gas syringe is compressed to half its original volume. So it's half its original volume while temperature remains constant. Which one of the following combinations are correct regarding the gas pressure and the average speed of the particles, right? So here in pressure, so if you reduce the volume, it means you are compressing. So generally, if we are compressing, it means the pressure has to increase. So now we're looking at option A and option C. So here, pressure increases with a decrease in volume. So there was a decrease in volume. So here, this one, B and D are the odd ones out. Already they are out. Then now let's look at the second point that says average speed of the particles. Okay, so the speed of the particles, they do not change. They do not change. So this one says increases. The average speed of the gas particles are actually going to remain the same. So the correct letter for 1.7 is going to be A. Then we move on to question 1.8. 1.8 reads, consider the reaction below. So we're having 2S, which is a gas, plus SO2, which is a gas, then to give us a product, which is S3, S, and then H2, H2O, right? So which one of the combination regarding the reducing agent and the oxidizing agent so is correct in this reaction is actually correct, right? So now what is a reducing agent and what is an oxidizing agent, right? So a reducing agent is the substance that which is actually being oxidized and itself is being reduced. So if you look at this H2S versus SO2 according to the equation there, right? So what is actually going to happen here is that our H2S, according to this, is an agent, is an agent. Your H2S, this H2S is the agent. It's actually going to be the agent of it facilitates, for it to be called an agent is because it facilitates this other atom, this other compound to be what? To be oxidized. Without this one, we cannot have SO2 being what? Being reduced. So an agent is something that actually facilitates the process, right? So this is a reducing agent because it facilitates what? The process. So H2S and SO2 becomes our reducing agent as well as our oxidizing agent respectively. So H2S is the reducing agent, while our SO2 is actually going to be our oxidizing agent. Then 1.9 says, which one of the following has polar covalent bond but has only London dispersion forces between its molecules, right? So if you look at option number 1, NH3, right? NH3, remember we talked about FON, FON, where we're actually having our hydrogen bonds. So now here the question says, which one of the following has got a polar covalent bond but has only London dispersion forces between its molecule, right? So automatically you can count this one out as being having hydrogen bonds. Then we also have another one, which is HBr, then carbon dioxide, then H2S. So the old one out here is actually going to be our carbon dioxide. So which one of the following is polar? So carbon dioxide has got polar bonds. Carbon dioxide has got polar bond, but has got only London dispersion forces between its molecules. Then we move on to 1.10, which is 1.10. Consider the following incomplete reactions. The reactions are incomplete of H2SO4, sulfuric acid there. Now, if we were to put this one in terms of our product, if we were to work out our product, what we're actually going to have in this case here is we're actually going to have, it says which reactions will produce CO4 and water as the products, as the only products for this reaction, right? So it means here we're actually going to have CuSO4 plus water, which is your H2O, right? If you were to check this out, so your CuO plus H2SO4 there, it means how many coppers do we have? We have got copper and then this other copper, then your sulfur there, we've got your sulfur, then oxygen is 4 oxygens, and then this side is 4 oxygen, then 1 oxygen, so this one is fine. So option 1 already is in. So where there is option 1 is option C and A. So automatically it means B and D, they are already out. Then the second equation has got how many oxygen? So if we say CuSO4 plus H2O, let's try and work it out to balance. So copper there, we have copper as a product. Then your carbon, we don't have our carbon. So it means here we're actually going to need something which is more of a what? Of a carbon, and we don't need it, since here which reaction will produce carbon, the CSO4, copper sulfate, and water only. So it means this other product that is actually going to be formulated is not necessary. So it means equation number 2 is also out. This one is actually out. So you are left with CuOH and plus H2SO4. So we need our product to be copper sulfate, CuSO4, plus your water, which is your H2O. So if we were to check this out, are there any other products that are actually going to be formulated here according to this? According to this, there are no any other products that are actually going to be formed. So the correct answer should be both 1 and 3. So the correct answer is C, both 1 and 3. Then we move on to question 2, which read, consider the following compounds. We've got NH3, which is your ammonia. Then we also have our S3O, hydronium ions, BCl3, NaCl, and HCN, your cyanide there, sodium chloride, and all. So it says define the term molecule, right? So for us to define the term molecule, we're going to say a molecule. This is a group of atoms. Molecule, it's a group of atoms, covalently bonded covalently bonded together and function as a unit. And function as a unit. That's the definition that you're actually going to have there. It says a group of atoms covalently bonded together and function as a unit. That's how we actually define a molecule, right? Then the statement reads, write down the formula, or we're looking for the formula of the compound from the given list that has got a dative bond, right? A dative bond. So the one that we're actually going to have as a dative bond is actually going to be H3O plus, right? Remember, in a dative bond, one has to actually give out, or they donate its electrons. So it's actually going to give out to the other one. So the one that can actually give out here and formulate a formula given the list, write down the formula of the compound from the given list that has got a dative covalent bond is actually going to be what? Our H3O or plus there. That's the one that actually formulates a dative bond. So remember, only there someone has to give or pay for the meals, if you were to put it like that. So in this case here, a dative bond, the one that can actually formulate a dative bond is H3O plus. So then the second question, 2.1.3, ionic bonds, ionic bond. So the one that actually formulates an ionic bond here is sodium chloride, right? Sodium chloride. Then 2.1.4 is ion dipole forces when dissolved in water. So whenever we dissolve in water, the one that forms an ion dipole force when dissolved in water is still again, this is NaCl, right? They can actually dissolve in water. So they actually formulate whenever dissolved in water, an ion dipole force is actually formed. Then draw the Lewis structure, 2.2, draw the Lewis structure for the following molecules. So we're having NH3 again. So having NH3 then, it means your N is the central atom there. Your N is central atom. So if you go to your periodic table, you find that nitrogen has got 5 electrons. So 1, 2, 3, 4, and 5. So at the top there, that's what you're actually going to have and refer to it as a what? A lone pair. So the top part there, this top part here, is the one that is referred to as the lone pair. Then on the other end, we're now going to add hydrogens because we're having how many hydrogens here? 3 hydrogens. So it means here we're actually going to have another hydrogen, first hydrogen, then the second hydrogen, and then the third hydrogen like that. So this is how we're supposed to draw the Lewis diagram, Lewis structure of the following molecules, which is NH3, right? So if we were to check here in terms of the one that are referred to as the bonding pairs, if we were to check the ones that are referred to as the bonding pairs, so it means this one here, these ones are referred to as the bonding pairs. Then the next question is 2.2, where we're actually going to draw the one for a cyanide, which is your HCN, right? So if we look at the HCN here, what you're actually going to have is something like this. So your carbon becomes the central atom. So your carbon becomes the central atom. This is your carbon. And then remember, this is your hydrogen. So it means hydrogen has got how many electrons on this outer shell? It has got only 1. Then carbon has got 4. So amongst these 4, it means this other one, the first one, is actually going to bond with a hydrogen. And then these other 3, 1, 2, 3. So formulating for, remember, carbon is carbon chiral. It means it has got 4 electrons on this outer shell. So these 4 here, these 3 here on the other end, they're actually going to bond with these other 3 for nitrogen. For example, remember nitrogen has got how many? 1, 2, 3, 4, and 5. So these three that are actually like referred to as the bonding pairs. These 2, 3 are the ones that are actually going to attach to what? To this carbon. So it means here 1, 2, 3. So these are the bonding pairs. Then your nitrogen, then you're also going to have your other 2, which are referred to as the lone pair. So this is the structure of HCN, which is your cyanide, in terms of what? A Lewis structure. Then now we're asked, how many lone pairs for question 2.3? How many lone pairs of electrons are in one molecule of NH3, right? So if we are looking at that at the top there, we can see that how many lone pairs are there? We already identified them as being only one lone pair. So we've got one lone pair and three bonding pairs in terms of this one. So at the end of the day, our answer is actually going to be one lone pair. Then we move on to question 2.4. Is BCl3 a polar or a non-polar molecule? Is BLC a polar or a non-polar molecule, right? So BLC3 is a non-polar molecule. Then we're supposed to explain as to why BCl3 is a non-polar molecule, right? So here, in terms of like explaining, we're going to say BLC3 is actually BCl, start there, is actually polar. Then the electronegativity values, right? BCl is actually polar. But then in terms of the electronegativity values, En, delta En, so you can go to your periodic table, you'll see your electronegativity values, you'll find that is 3.0 minus the 1, which is actually 2.0, 2.0, and then you will get a 1 there in terms of this. So let's just like go through our periodic table and see what you actually have on our periodic table. Periodic table. So we are actually going to get a value of 1. But for BCl3, what we're actually having here is actually going to be what? A trigonal. A trigonal. So if we're having a trigonal, it means now molecules, 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 or the molecule, because it's BCl3. So molecule is actually symmetrical. Symmetrical. It's actually symmetrical. And then polar bonds. Cancel each other. So in terms of explaining this one, so BSC is trigonal. Since it's trigonal, so the molecule is actually what? Symmetrical. Since it's symmetrical, then the polar bonds, they cancel out each other. So making it out formulating a non-polar molecule. Then let's move on to the next question, which is question 2.5. So question 2.5 reads, the graph below shows the relationship between potential energy, so this is the potential energy, and the internuclear distance between two hydrogen atoms, right? So now we've got the internuclear distance, then here we've got potential energy in kilojoules per mole, then we've got points labeled A, B, and C, right? So before we move on, by just interpreting the graph, we will find that like, since they're saying the relationship between energy and internuclear of two hydrogen atoms, right? So we're having two hydrogen atoms. So it means here at C, I can put this hydrogen and then this other hydrogen. We're saying these two are actually what? Approaching each other there at point C there. That's where they are approaching each other. Then here, once they get to B, they're close to each other. And B, they're close to each other. Close to each other. Here, they will formulate something like that at B there. So here, they were approaching each other. Then here at A, it means they're too close to comfort, and then they actually are separate. So at B there, that's what we actually have in terms of the structure. Then the first question says, define the term bond energy. So bond energy is the energy needed to break 1 mole, break one 1 mole, 1 mole of a compound's molecule into separate atoms, into separate atoms. That's how we define bond energy. So now, according to this, we've been asked which point 2.5, which point A, B, or C in the graph represents the point of maximum force of attraction between the nuclei of the two hydrogen atoms. So those are the points that we're actually having. So which points A, B, or C on the graph represent the point of maximum force of attraction between the two nuclei of the two hydrogen atoms? So the correct answer there is B, this part B here, B. So the answer is B. So they are close together. Remember A and point C, they are approaching to each other. Then B here, they are now close to each other. That's where we are. Then 2.6, it says, consider the following table. Consider the following table. Consider the following table. Which one of the bonds shown in the table above will have the shortest bond length? Which one of these will have the shortest bond length? Remember the bond order here, we're having only one, then here's a double bond, here is a triple bond, right? According to the bond order, it means the one that is actually going to have a shortest bond length is actually going to be what? C, this one. The one that has got a triple bond. So which one of the bonds shown in the, so it's the one with the triple bond there, right? So bond energy, remember we defined bond energy as the energy needed to break 1 mole of a compound's molecule into separate what? Atoms, right? You'll find like here, there is more energy that is actually required for this one. So it means they are closest together. So the triple bond is more tighter than this other one. It means more energy is actually going to be required to what? To overcome it, right? Then we say the reason. They are saying give a reason for your answer to question 2.6.61. So the reason behind it says higher bond energy. We've got a higher bond energy here, higher bond energy. It has got a higher bond energy, as you can see, it has got an energy of 835 kilojoules per mole. So it means, what does that mean? Higher bond energy. It means it has got a stronger force of attraction. Therefore, there is a stronger force of attraction, Then after that, we need to explain in terms of the nuclear. So since these are closely together, now the bond energy is higher, then close stronger force of what? Of attraction. So if these two, they are attracted towards each other, it means the nuclei gets closer. The nuclei gets close together, gets closer together. Therefore, shorter bond length. So according to this, we can see, since it's a triple bond, more energy is required to overcome it. Then higher bond energy, stronger force of attraction. There's going to be a strong force of attraction between this triple bond. So once there's a strong force of attraction, it means the nuclei, they get close together. And then once they get close together, it means now what happens, the bond length also decreases or becomes shorter. In question 3, we're having the table below shows the boiling points of group 4 compounds. So we're having group 4 compounds. So we're having CH4 boiling point, which is a negative, 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 a negative, until we reach a compound E with a boiling point of X there. Then it says define the term boiling point. So when it comes to this definition of terms, it is very important for you to master them because they carry valuable marks. So for us to define boiling point, we always start with the temperature, says the temperature. So if you omit this part that says the temperature, you're actually going to lose your marks. So is the temperature at which the temperature at which the vapor pressure, at which the vapor pressure of a liquid equals its atmospheric pressure. Like that. So now it says 3.2, write down the phase of compounds A to D at a room temperature. So we need to know the phase. Are they in liquid, solid, or gas, right? So write down the phase of compounds A to D at room temperature. So now look at this. They are already boiling. Here at a negative, they are boiling. At a negative, they are boiling. At a negative, they are boiling. At a negative, they are boiling until they A to D, right? So until D at a negative is boiling. So it means all these, they are in a gaseous phase already because room temperature is considered at around 25 degrees Celsius, right? So if we are having a temperature which is positive and all these, they are already boiling in a negative, at a negative temperature, it means here already they are actually going to be what? To be gases. So the answer here is actually going to be a gas. Then 3.3, explain the trend in boiling points of compounds A to D. So the trends in boiling points of compounds A to D, right? If we were to look at compounds A to D, what we're actually going to have here is that there is generally, if you look, there is actually generally an increase as you're moving from A to D. There is an increase in terms of what the boiling point in from A to D, right? And also the molecular size. We can start with the molecular size, right? So question 3.3, we can say the molecular size increases from A to D. We can say from A to D, right? So what happens if this molecular size increases? It means also London forces increase. So London forces increases, then the other bullet is actually going to be O on energy, right? So what happens if this London forces increases? So it means their strength is increasing. So once their strength increases, it means here what we're actually going to need, we need more, a higher temperature. And then that's how the boiling point is actually going to be affected. Since this is now affected, it means we're actually going to require more energy. As a conclusion, more energy is needed to overcome intermolecular forces in D than in A. So as you see the trend, if we are to go back to the trend, you'll see like temperature has been increasing, -16, -12, -88, -52. So you'll see that D has got a higher boiling point than A. You will notice that molecular sizes increases from A to D, London forces increases as you are moving down. Then it means more energy is needed to overcome intermolecular forces in D than in A. More energy is needed for you to overcome the forces in SNH4 than the one in CH4. Then we move on to question number 4. Question number 3.4. So 3.4 reads, which compounds in the table A to D will have the highest vapor pressure? Which compounds A to D will have the highest vapor pressure, right? So the one that has got the lowest boiling point is the one that is actually going to have the highest boiling point, vapor pressure. So the higher the boiling point, the lower the vapor pressure. So they are inversely proportional. They are inversely proportional. When you have got a higher temperature, it means we are actually going to have a lower vapor pressure, right? So now, having that said, which compound in the table A to D will have the highest vapor pressure? So you can see A has got the lowest BP, which is your boiling point, is the lowest boiling point. It means it's actually going to have the highest vapor pressure. So according to this information, you'll see whenever you have got a lower BP, you are actually going to have a higher VP. So according to this information, so which compound in the table will have the highest vapor pressure? You could have guessed this one and got it correct. So it means the letter A is the one that is actually correct there. A is actually going to have a higher or the highest vapor pressure. Then they say give a reason for your answer by referring to the data in the table. We have already explained there in terms of the lowest. It has got the lowest boiling point. Therefore, because it has got the lowest boiling point, it's actually going to be having a higher or the highest vapor pressure. Remember, they are more of like inversely proportional. Whenever the boiling point is high, it means the vapor pressure is actually going to be what? To be the lowest there, according to this information that we're given. Then 3.5, how will the value of X, this value of X, this X here, how will the value of X compare to the boiling point of C4, right? So the value of X, how will be the value of X? So choose from higher than, lower than, or equal. So automatically, C4 has the lowest boiling point. So as you are going down, you can see the trend. As you are going down, as you are moving down here, what happens to the boiling point? Boiling point also what increases. So it means automatically X is actually going to have a higher than. So the correct answer there is higher than 2. Then now 3.6, we're supposed to explain the answer. It says fully explain your answer to question 3.3.5. So in terms of the forces, we know HCl is actually going to have a dipole forces. So this one has got a dipole forces. Then CH4 is a London force. Then now dipole DP, dipole forces are stronger than London forces. Then at the end there, you're going to say more energy is a conclusion. More energy is needed to overcome dipole forces than London forces. So this is what we're actually going to have, right? So in terms of their strength here, or in terms of answering this question, which is your 3.6 there, what you can also start with is the eyes. Right? So you can start with the eyes like that, right? So it means the eyes there is the intermolecular force. Try and identify the intermolecular force. Let me erase the intermolecular forces, right? Then after that, the second bullet, we are supposed to compare these in terms of their strengths. Then E is for energy. Explain in terms of the energy needed to overcome. So take note of this term overcome. We're not actually going to use the term to break. We overcome intermolecular forces. More energy is needed to overcome intermolecular forces. IMF, I'll write it as IMF there in dipole forces than London forces. So that's how they are. So in terms of their strength here, we have got the London forces, then we have got the dipole, as I just said, DP. Then at the end there, you're actually going to have your hydrogen bond. So the London forces are the weakest. So as we are moving to the right, the strength of the bond actually increases. So London forces are the weakest, followed by dipole forces. Then hydrogen bonds are the strongest. So as we are moving to the right, the strength of the intermolecular forces increases. Then we move on to question number 4. A group of learners investigate the relationship between the pressure and the volume of a gas. So it's the relationship between the pressure and the volume of a gas. So the syringe, the gas syringe is connected to apparatus X, as shown in the shown below. So apparatus X there, then we have got our syringe there. Then it continues to read the learners vary the volume and record the pressure and volume. So they calculated the inverse of the volume and recorded it with the pressure readings in the table below. Then that's the table that they actually have there. They have got their pressure in kilopascals. Then the next one is volume, the inverse in cubic centimeters there. Then here we're actually going to have the first one until number 4, right? So it says, write down the name of the gas law that is being investigated, right? So it means here what we're investigating is Boyle's law. That's what we are investigating here. They are investigating Boyle's law. So for this investigation, write down one controlled variable, right? So the control variable, when it comes to this, they maintain a temperature. The temperature should always remain the same, right? So remember, if you increase the temperature, what happens to the particles? Particles get to gain kinetic energy. Once they gain kinetic energy, they become excited. Once they get excited, they start moving around. So it already changes around, changes everything whenever the temperature is actually compromised. So here, for this investigation, the control variable should be our temperature. Control variable is our temperature. Then whereas the name of the apparatus X. If we look at X, there you can see it's a gauge. It's a gauge. What are we trying to measure? Measure pressure. So at the end of the day, apparatus X is referred to as a pressure gauge. Like that. So apparatus X is a pressure gauge. Then 4.4. Use the data in the table and draw a pressure against the inverse of volume graph on the attached answer sheet marked annexure A. So we're supposed to draw a graph, okay? So according to this, what we're actually going to do is try and sketch. I will actually sketch this one out. So this is what we're actually going to have as our graph there. We're actually going to have, let me try to make it a bit straight. So here, this is what we're having there. And then here, we're actually going to have our pressure. Pressure in kilopascals. Then at the bottom there, we're going to have this inverse, the one that is actually given there at the top. It's 1 over V, 1 over V, 1 over V. Then the units of measurement is like that. So this is what we're actually going to have there. Then to sketch this one, it means here the pressure on the y-axis, and then the other one, the volume there, the inverse is on the x-axis, right? So if we are to look at here, we're starting from 0.05 until 0.08. So what we can actually do is formulate a scale, maybe from 0 here, it can be 0.0 to 0.04, 0.06, 0.08, like that, right? Then on the other end, if we're to look here, we're starting with 148, 129, 111, 92. So here, the lowest value, the smallest value is actually going to be 92, then higher. The highest is going to be 148. So here we can actually start with a scale of maybe, let's say, 50, 50, 50, 100, 50, 100, 150, and then 200. Like that, right? So at the end of the day, what you're actually going to have is a straight line graph. So if you look at this, so we're saying pressure of 92. So pressure of 92 is somewhere there. So if we were to have a pressure of 92, a pressure of 92. So what you're actually going to have is an inverse of 0.05. So 0.05, this one goes with 0.06 somewhere there. Then here we're actually going to have a line there. Then the other one goes with 0.06, 0.06, and 111. So above there, we're actually going to have something there. Then the next one is 129, just below 150 there. And then what do we actually have in terms of the volume is 0.07. So in between this, then the last one, 0.08, and then we're actually going to have 148. So at the end of the day, we're actually going to have a graph that starts from there and goes straight like that. So you must actually formulate a graph that looks like that. Then we move on. It says, using the information from the graph, write down the learner's conclusion. So here, according to this information, you can see whenever you are increasing the pressure or pressure is inversely proportional. Pressure is inversely proportional to the what? To the volume. That's what we can actually conclude from the graph. That pressure is inversely proportional to the volume. Then 4.6 reads calculate the volume of the gas at a pressure of 184 kilopascals. Calculate the volume of the gas at a pressure of 184 kilopascals, right? So our formula here to calculate this one is P1 V1 is equivalent to P2 V2. So the first pressure, P1. So we're actually going to pick values. I'm actually going to use a experiment number 4 there, 4 there. So I'm actually going to say the pressure, my pressure is 148. 148. Then the volume there, we're told it's 0.08. But remember, this is an inverse. So it's supposed to be 1 over multiplied by 1 over 0.08 is equivalent to, so now we are asked to calculate what? The volume. So it means this V2 is the one that we are looking for, but here the pressure is actually given as 184. So it's going to be 184, then multiplied by V2. So at the end of the day, we're supposed to make V2 the separated formula. So your V2 is actually going to be, if we divide, we're actually going to get 10.05. 10.05, 10.05, like that. So if my math is correct, we should be getting 10.05. So the volume there, what's the volume? It's 10.05, like that. Then we move on to question 4.7. 4.7, what we're actually having here is the graph of pressure versus the graph of pressure versus the volume of an element. The graph of pressure versus the volume of an element. The graph of pressure versus volume of an enclosed gas at a constant temperature for a real gas and an ideal gas is shown below. Then explain, it says explain the deviation of a real gas from an ideal gas. So we need to see the deviation of an ideal gas from a real gas. So what's the deviation? What's the deviation there? So if you look at this graph, it means we're having an ideal gas there. The first one is an ideal gas, then the second one is a real gas, right? So explain the deviation of a real gas from the ideal gas behavior as shown in the graph above. So how does it deviate? So you'll see that it's there. What happens to the pressure? As you go up, pressure increases, right? As you go up, pressure increases. So it means at high pressure, what happens at high pressure? It's higher or high pressure. Erase that one. It's high pressure. It's high pressure. Real gas. Real gas particles become significant. So we'll find that at high pressure, real gas particles become significant. Then it says, give one reason in terms of the type and strength of intermolecular forces why ammonia gas NH3 will deviate from the ideal gas at a low temperature. So if you look at NH3, it already has hydrogen bonds. So hydrogen bonds are strong. So the reason behind is because it has got NH3. NH3 it has strong hydrogen bonds. That's the reason. That's the reason why we're having that. Then we move on to the next question, which is question number 5. So question number 5 reads, 1.56 grams of calcium carbonate is heated as shown in the diagram below. So we heat this calcium carbonate. How many grams? 1.56, and then is heated as shown in the diagram below. Then it says the calcium carbonate decomposes according to the balanced equation. So we're having this reaction, calcium carbonate, which is a solid, gives us calcium oxide, which is a solid, and carbon dioxide, which is a gas. Then we have got our delta H greater than 0. So if your delta H is greater than 0, they automatically know that this is an exothermic reaction. What does that mean? It means it gives out heat to the surroundings, right? An exothermic reaction gives out heat to the surroundings. So now it continues there. It says 0.163. So now we're having 0.163 of carbon dioxide is produced during this decomposition. Right? So the first question read, is this reaction endothermic or exothermic? We're already shown there. We're saying the reaction is actually going to be exothermic. So in terms of this now, 5.1.2 says, give a reason for your answer in question 5.1.1. So the reasoning behind why we're saying this is exothermic, you can just say delta H. Your delta H is greater than 0. Or you can say your delta H is positive. Delta H is positive. So these are one and the same reason. So we can just say automatically your delta H is greater than 0, or you can say your delta H is positive. Then we move on to question 5.1.3. Describe Avogadro number. So Avogadro number refers to the number of particles in one mole. So Avogadro number is the number of particles in one mole. So we are done with the definition there. Says 5.1.4, it says calculate the number of carbon dioxide molecules produced. Calculate the number of carbon dioxide molecules produced. So now, to calculate this, what we actually need, the number of molecules. So we're looking for the number of molecules that are produced on this one. So what we're actually going to do is use the upper part there, top part, this part here, to calculate the number of particles. So now what we're actually going to have is number of moles, right? N is equivalent to M over molar mass, right? So that's where we're actually going to start. The reason why we're going to start from there is because already what we actually have there, we're looking for the number of moles according to this. So the data is like this. So the data here, that's what we are given. N is equivalent to question mark, then the mass, and then the molar mass. So the mass there that we're actually given is 0.163. 0.163. 0.163 there of carbon dioxide, right? So it's going to be 0.163. And then the molar mass for this one is actually going to be 44. 44. 44, because if you say carbon, has got a mass of 12, then 16, 12 plus 60, 32, which is 44. So we're having 44 there. Therefore, now we can automatically substitute into our formula. Therefore, your N is equivalent to the mass that we're given is 0.163 all over the molar mass. The molar mass is actually 44. So if we divide that one, what do we get? We say 0.163, 0.163 divided by 44, we get an answer of 3.7 times 10 times 10 exponent negative 3, like that, right? This is what you're actually going to get. So which is same as, or in terms of decimal, it's actually going to be 0.0037 moles. So this is what we're actually having there. Then having said that, now what are we looking for? We've been asked to calculate the number of molecules. So for the number of molecules, we're actually going to use a different formula for the number of molecules. So now what we actually have are the number of moles there. So having the number of moles now, we're supposed to calculate the number of molecules, right? So for the number of molecules, we know N is equivalent to N, capital letter N is equivalent to N, Na, like that. So if we were to do this one, therefore we're actually going to say your N is equivalent to the number of moles that we actually have here is 0.0037. Then we multiply it by the Avogadro constant, which is 6.02, 6.02 times 10 to the power of 23, like that, right? So if we do our math there, we multiply, we are actually going to get 0.0037 multiplied by 6.02 multiplied by 10 exponent of what? 23. So what we're actually going to have is an answer of 2.227 times 10 times 10 to the power of x naught, exponent 21, right? So what are we looking for there? We're looking for molecules, number of molecules produced, right? So we can say, just say the molecules, like that. Then we can now move on to question 5B, 5.14B. It reads, calculate the mass of calcium carbonate that remains unreacted. So we're looking for the mass of calcium carbonate that remains unreacted in the flask at the completion of the reaction, right? So once the reaction is completed, what is it that is actually going to remain? At the completion, calculate the mass of calcium carbonate that remains unreacted in the flask at the end of the completion of the reaction. So let's work it out here. So we need the mass of calcium carbonate, right? So to start with, we need to start with the mole ratio. So let's just say mole ratio. So what are we having here? According to the information at the top there, what we're having here, the mole ratio between calcium carbonate and the one for carbon dioxide. So calcium carbonate. So if you look here, so 1:1. So the mole ratio is 1:1. So I'm actually going to say the CO2 is to the 1 for CaCaCO3. So CO2 is to CaCO3. So according to this one, you know the mole ratio there is 1:1, right? So now if we're having 1:1, if we are to go back at the top, a bit at the top there, when we were asked to calculate the number of moles, right? Calculating the number of moles. So these were the number of moles for carbon dioxide. So what did we get? We got 0.0037, right? So what does that mean? If we're having 0.0037 on this other end, so the mole ratio is 1:1. So automatically we should be having 0.0037 on this other end, like that, because the mole ratio is actually 1:1. So now to calculate the number of moles for calcium carbonate, so we're actually going to say number of moles is equivalent to M over M, mass over the molar mass. Therefore, this is equivalent to 156, because we're given 101,56. 1,56 here, we're given 1,56 of calcium carbonate, right? That's the mass that we're actually going to have. So it's 1,56 all over the molar mass, right? So the molar mass for calcium carbonate, we're actually going to say on the side here, calcium is equivalent to, is it 40? Then we have got your carbon, which is equivalent to 12. Then we have got your oxygen, which is equivalent to 16. So here, calcium multiplied by 1 will remain the same. And then your carbon is also only 1. Then this one multiplied by 3, right? So if we add all this, we should actually get something like 100, like that, right? So if we divide that one, 1,56, 1,6, 1,56, 1,56 divided by 100, what do we get there? Got an answer of 0.0156. So this is equivalent to 0.0156 moles. So these are the number of moles that we are actually having there. Therefore, now the number of moles that are actually remaining, let's create some space here. The number of moles that are actually remaining, we're actually going to say number of moles remaining, the second part. So the number of moles remaining is equivalent to 0.0156 minus 0.0037. So the difference between these number of moles and the ones that according to the mole ratio, that's what we're actually having as remaining. So if we subtract the minus 0.0037, we're actually going to get a value of 0.0119. So this is equivalent to 0.0119 moles. So these are the remaining moles that we're actually having, right? But according to this question here, says calculate the mass, right? So mass of what? Of calcium carbonate, right? So here, what we're actually having here are the number of what? Of moles. So if we're going to go back again, we're going to say N of what? CaCO3 is equivalent to M again, all over M, right? So the number of moles that we already have remaining there is 0.0119 is equivalent to the mass of calcium carbonate. So the mass of calcium carbonate there is actually that's the one that you're looking for, the mass. Then the molar mass here is actually 100. So we make M the subtotal formula. Therefore, your M is equivalent to 0.0119 multiplied by 100. So this is equivalent to the final answer. If we multiply the 0.0011 multiplied by 100 is equivalent to 1,19. So your answer is 1,19 grams. That's the final answer that we have for this one. So the mass of calcium carbonate that remains unreacted in the flask at the completion of the reaction is equivalent to 1.19 grams. Then we can move on to question 5.2, which reads, A compound with a molar mass of 162 grams per mole has the following mass composition. Then we're asked to determine the molecular formula of this compound. So we have got carbon, which is 44.4%. Then we have got hydrogen, 6.21%. And then sulfur, 39.5%. And then the last one, which is oxygen, which is 9.86%. Right. So to calculate this one, we're actually going to formulate. I will erase to create space there. We work it out at the bottom. Erase. And remove all this. And as I formulate the table so that we can work it out. So now, take note. For you to be able to determine the molecular formula of the compound, you need to go through the empirical formula, which is your simplest ratio. So we're actually going to start by working out the empirical formula, which is your simplest ratio. Then after that, we can be able to work out everything. So we're actually going to formulate a table, the one similar to what they actually drew here. They started with carbon there. We're actually going to draw a table like that. Then carbon. Then here, what do I have? I have got hydrogen. Then the next one is sulfur. Then the last one is going to be my oxygen there, right? So according to this information, right, the percentage can be converted to the mass. I can just say this is the mass. So I can just say M here, mass there. Then we're actually going to start with, let me just widen this line here. Make it a bit bigger. Yes, like that. Okay. So now what we are having here is 44. So we just take this one as 44.4. Then this other one, we're told is 6.216,21. Then for sulfur is 39.5, 39.5. Then for oxygen is 9.86. Right? These are the masses there that we're actually having. So then the next step, we're supposed to do the number of moles. So remember, for you to calculate the number of moles, N is equivalent to M all over M. So for carbon there, it's actually going to be 44. 4 all over. Carbon is carbon 12. Then this one is hydrogen 6.21 all over. Hydrogen has got 1. Then 39.5 all over. I think it's 32 for sulfur. Then oxygen is 9.86 all over. Oxygen is 16, like that, right? Then let's do our math there. Make use of our calculator. 44.4 divided by 12. Then we get 3.7. So a value of this is equivalent to a value of 3.7. Then this is equivalent to retains 6.21. Then this one, 39.5, 39.5, 39.5 divided by 32. 32, what do we get there? 1.23. So we're actually going to have 1.23 here, 1.23. Then the last one, which is our oxygen. Our oxygen 9.86, 9.86 divided by 16. And then what we get there is 0.62. If rounded off, this is given 0.62 like that. So this is what we're actually having there. Then after that, we need to find the ratio, the mole ratio. So according to this, I'm just going to say ratio there. Therefore, now, for us to find the ratio, we divide by the smallest number of moles. So all these are moles here. These are the moles. These are the moles that we're actually having. So here, the smallest one is 1.23. So it means here we're going to say 3.7 divided by 1.23. Then we move on to 6.21, also divided by 1.23. No. The smallest value is 0.62. Smallest value is 0.62. 0.62. So we divide there. It's supposed to be 0.62 all over 0.62. Then here also we're having 1.23 all over 0.62. 62, not 63, 62 there. Then we also have 0.62 all over 0.62, right? So if we are to divide all these, the other one is actually going to retain. Here is going to be 1. Then we divide 1.23 divided by 0.62. What we get there? We're actually going to get a 2. A 2. Then 6.21 divided by 0.62. 0.62. What we get there? We get a 10. So this one is going to be a 10. Then the other one, 3.7, 3.7. Then we divide by 0.62, 0.62. Then we're actually going to get a 5.96, which can be converted to a 6 like this, right? So this is what we're actually having there is the simplest ratio. This is what we're actually going to have, right? So here, if you go back at the top there, you will see that the ratio there is actually 1:1. So at the end of the day there, if we are to look at it, we're actually going to have an empirical formula of C carbon is C6, then hydrogen there, we're having 10. Then here for sulfur, what we're actually going to have is 2. And then for oxygen is equivalent to just, there's no need for us to write in order a 1 because it's actually going to give us the same. So that's how we're actually going to get our final answer there. Since the ratio is 1:1, according to this 162, then it means at the end of the day, we're actually going to have retain C6H10, S2, and then oxygen. Then question number 6. Question 6 reads X grams. So unknown grams there. We're having unknown grams of sodium, unknown grams of sodium, carbonate Na2CO3 reacts with 0.028 moles of hydrochloric acid, HCl. Then at 25 degrees, the balanced equation for the reaction is, we're given the balanced equation for the reaction. Then here we are told 448 cubic centimeters of carbon dioxide gas is produced during this reaction. The molar volume at 25 degrees is 24.47 term cubed per mole. Define the term limiting reagent, right? So this is a limiting reagent is the substance that is actually completely used in a chemical reaction and determines the amount of product that is being formed. So we're going to say substance that is completely used up in a chemical reaction, and determines the amount of products formed. Perfect. Okay, so now that's how we state or define the term limiting reagent. So that substance that gets used up, completely used up within a reaction, a chemical reaction, and is the one that also determines the amount of product that is going to be produced or formed. So 6.2 reads, name the law that states that 1 mole of any gas occupies the same volume at the same temperature and pressure. So this is the Avogadro. Avogadro, that's the law. Avogadro's law states that 1 mole of any gas occupies the same volume at the same temperature and pressure. Check this out. Temperature and pressure. So if you change the temperature, everything changes. Then by calculations, we've been asked to determine which substance is the limiting reagent. So it's between NaC, Na2CO3, which is your sodium carbonate, and your HCl, which is your hydrochloric acid there. Therefore, now let's work this one out. So to start with, we are given the volume. So we're given the volume there is 448 cubic centimeters of what? Carbon dioxide. And then the molar gas volume we are also given is 24,47. Check this out. So most of the times we are given it is 22.4 cm cubed. Most of the times, if it's not stated there, we're actually going to go to the data sheet and extract 22.4 cm cubed. But in this case, we've been given. So whenever you're given, you are supposed to use the value that you're actually given. So according to this, if we say the number of moles, so we're given the data there, which is our 448 cubic centimeter of our carbon dioxide, right? So we've got the volume. So according to this number, we can say number of moles of CO2 is equivalent to, so if given this one, we cannot say M over M because these are gases. So we're going to say V all over Vm like that. So now to convert this one, what we actually have there, the volume there we're told is 448 cubic centimeters. Remember the units of measurement for this one, 448 cubic centimeters should be in dm cubed. So to convert to dm cubed, we're going to say 448 cubic centimeters, then divided by 1,000. So if you divide by 1,000, we're actually going to get 0.448 dm cubed. So now we have converted to dm cubed, the one that we are supposed to use. So now we can automatically substitute. Volume there is going to be 0.448 over the molar gas volume, Vm there. Remember, we are given. So we're not going to use 22.44, but we're actually going to use 24.47. So if we divide that, we're actually going to get 0.0. Let's see. It's going to be 0.448 divided by 24.47. So the equivalent there is 0.018. So this is equivalent to 0.018 moles. So these are the moles of what? Of carbon dioxide. These are the moles of carbon dioxide. Then the next step here, we're supposed to calculate the mole ratio. Now, what you are actually having here, let me erase, create space, remove the conversion. So remember to convert from cubic centimeters to dm cubed, you divide the given value by 1,000. By 1,000. Okay. So now HCl versus Na, HCl versus sodium carbonate, Na2C, so 2 the CO3, right? So according to the balance equation, if you look here, we're having 2, here we're having 1. So they were having 2, this is 2, and this other end is actually going to be 1, right? So now, having that, we're actually going to say the mole ratio is 2 is to 1. So here, what are we actually having here? The number of moles of carbon dioxide is 1. For carbon dioxide is 0.018. And then if it's 1, so it means the number of moles of sodium carbonate is also going to be 0.018. So 0.018 on the other end. So if this is 1, according to this mole ratio, so we're having this versus the one for carbon dioxide. So here is 1 is to 1. So it means the number of moles for this one and this one for carbon dioxide, they're the same. That's why we're actually going to take 0.018 and make use on this or of it on this other on this other end. So that's 0.018. So then it means, what does that mean? It means this one is half of this other one. So if it's 1:2, then it means here at the end of the day, what we're actually going to have is 0.09. So if it's 0.09, so remember the number of moles of carbon dioxide, number of moles of CO2 is equivalent to the number of moles for Na2CO3. So if we've got this information, now we can actually deduce according to the mole ratio what we are supposed to make use of. Therefore, given that HCl is to 2 and then the sodium carbonate is to 1, so now we can actually formulate or deduce that the number of HCl is equivalent to the number of HCl. So we can say the number of HCl there, the one that is actually required, is going to be equivalent to half the number of what? Of 0.018 moles. Like that. So if we're having the half, it means at the end of the day, this one that is actually required is actually going to be 0.009 moles. These are the moles for HCl that are actually going to be required there. Then after that, now, if we're having that, then let's compare with what is actually available. What is actually available is number of moles of HCl, available is equivalent to 0.028. So those are the number of moles that are actually available for HCl. Then after that, now we're supposed to say, after these conversions, we can now see which one is available and how many are not are required, right? So we are comparing what is available versus what is actually required. So what is available versus required? So this is what is actually available, and then the required is 0.09. So the required is 0.09, then the available is 0.028. Therefore, now, according to this, we can now see that Na2CO3 is the limiting reagent. Can conclude that Na2CO3 is the limiting reagent. Then we move on to question number 6.4. Question number 6.4 focuses on the value of X. If you can go up a bit there, it says X grams of sodium carbonate. So that's where we are. X grams of sodium carbonate. So now, for us to find the value of X, we're actually going to use the number of moles of what? Of carbon dioxide. So N of CO2 is equivalent to the number of moles of sodium carbonate, Na2CO3, according to the equation. And then we saw that it's equivalent to 0.018. So having that 0.01.8, then we can say the mass for Na2CO3 is equivalent to N M, like that, right? Then if we were to substitute with the number of moles there, we are going to say 0.018, then multiplied by, so if we do our math there, our M there for Na2CO3, we're actually going to say sodium 23 multiplied by 2, then plus carbon, which is 12 multiplied by 1, and then plus oxygen, which is 16 multiplied by 3. So if we do our math there, 16 by 3 plus 12 plus, so we're actually going to get a value of 106. So 106. So this is equivalent to 106. So here we're actually going to multiply by 106. So 106 like that. So if you multiply that one multiplied by 0.018, then we're actually going to get a value of 1.90, 1.90 or 1.90808 grams, because this is the mass. This is the answer that you're actually going to get. Then now we move on to the next question, which is question number 7. So consider the following reaction. So 4NH3, we started with 4NH3 there plus 5O2, then reversible reaction. Sometimes we are asked about this symbol. It represents a reversible reaction. Reversible reaction. Like that. Then plus 6H2O gas, then to give us a delta. So you see the value there is negative. So if it's negative, we need to be able to know, is it going to be an endothermic or an exothermic type of a what? Of a reaction, right? So now it says now the graph below shows the potential energy against the cost of reaction or cost of this reaction. So this is what we're actually having there. Then define the term activation energy. So activation energy is defined as the minimum energy required to start a chemical reaction. So the minimum, this term is usually underlined, the minimum energy needed or required needed to start a chemical reaction. So if you leave out minimum there, just like no, you have lost your marks. Then what do the following sections of the graph represent? So we've got different sections of the graph. So we've got they started with RP, RP there. So RP there usually is the enthalpy, which is your delta H there, right? So RP is going to be the enthalpy slash delta H slash heat of reaction. This is what we're having. Then QP from QP, this other part there. So QP represents our EA, activation energy. That's our EA there. Then determine by calculation the value of X. So we're looking for X there, right? So here, remember when calculating the value for X, we need to use the enthalpy equation, right? So delta H, according to the information, delta H is equivalent to H products minus H uh, delta H reactants. So we have got the energy of the products minus the energy of the what? Of the reactants. So if we go up there, we're given the value negative 2.7, 2.16, 216.7. So this is the enthalpy there, your delta H. So it means on this other end, you're going to say negative 216.7 is equivalent to, so the energy of the products. Can you see the energy of product? Energy of product is going to be what? Your X. So it means X minus the energy of the reactants. So if you look at the energy of the reactants, the reactants has got an energy of what? 400. So minus 400. Then after that, you are supposed to make X the substitute formula. So X is equivalent to the same as negative 400 plus, if I'm to transpose negative 400 plus, just that all over here. So it's same as X is equivalent to, it should be a positive, because if you are taking 400 to that other end, it's going to be positive. So it's negative 216,7 plus 400. So your X is equivalent to, if we do the math there, we're going to say negative 400 minus 216.7, then we get a value of 183.3. So your answer there is 183.3. Then don't forget the units of measurement are kilojoules, kilojoules per mole, like that. So that's what we're actually going to get there. Then just for another information at the top there, that's what we're actually going to have an activated complex at the top. At the peak of the graph, we have got our activated complex. Then the effect of a catalyst there, if we were to add a catalyst, it means our graph was actually going to appear like this. Then you see it lowers the activation energy. So activation energy is actually what? Lowered with this make use of a what? Of a catalyst. Then they usually ask, how does it do that? It actually lowers, it uses a path, an alternative route that uses less energy. So if you add a catalyst, which is a substance that actually speeds up the rate of reaction, after that, then you are asked, how does it do that? By using an alternative route that actually uses less energy. Less energy. Then determine by calculation the value of X. We are done with that one. Then what effect will the addition of a suitable catalyst to the reaction mixture have on the activation energy of the reaction? So it says choose from increase, decrease, or no effect. So it decreases, it decreases, it decreases. So the effect of adding a suitable catalyst, it decreases the activation energy. Decreases the activation energy. So as indicated there, I've already drawn. So remember, your activation energy starts from where the reaction starts until there, the peak there, at the peak there. So if you look at this one, so where is your peak here? It means your peak actually ends like that. Then we move on to the next part that says 60 cubic centimeters of NH3 reacts completely with 90. So having 60 reacting with 90 of O2, then at the same temperature and pressure in a container that can expand. Calculate the total theoretical volume in dm cubed of the gases present in the container at the completion of the reaction. So now we're actually going to work it out here. So we're actually going to start with the volume of oxygen. So V of O2 is equivalent to, according to the data that is actually given there, we are having a volume of oxygen. Let's go up a bit. Go up a bit. So the volume of oxygen that is actually provided on the question paper there. Let's go up and check the data there. So there, what are we actually having? We're having V for oxygen, which is according to the mole ratio, the ratios V for oxygen, volume of oxygen, and volume of nitrogen there and there. Then and then the one for what? For H2O. So these are the values that we're actually having there, right? So what we're actually going to do, we're actually going to start by checking at the volume of oxygen that is actually going to react. So the volume of oxygen that is actually going to react, O2, this is the react. The one that is actually going to react is actually going to be equivalent to 5/4 multiplied by 60, like that. That's 60. That we're actually given there. Then if you do the math there, we're actually going to get a value of, if you say 5/4 multiplied by 60, we get 75 cubic centimeters. Then we move on to the volume also of NO. So volume of NO that is actually formed. The volume of NO that is actually formed. So the volume of NO that is actually formed is equivalent to the volume of what? Is equivalent to the volume of NH3. So then, which is equivalent to what? To 60, according to the information that you're actually given there. 60, like that. Then after that, now the volume of H2O, the volume for H2O is equivalent to, that is actually formed, also is going to be equivalent to 6/4, 6/4 multiplied by 60, multiplied by 60. So if you do the math there, we're actually going to say 6 divided by 4 multiplied by 60. And the answer that we're actually going to get is equivalent to 90, which is equivalent to 90 cubic centimeters, right? So now this is what we're actually going to have. Then after that, now we need to see what is actually remaining. So the volume of oxygen that is remaining, the volume of O2, the volume of O2 that is remaining is going to be equivalent to 90 minus 75. So if you subtract that one, we're actually going to get 15 cubic centimeters. 15 cubic centimeters. Then after that, now the volume, the total volume for this is actually going to be 15 plus 60, 15 plus 60 plus 90. So if we add 15 plus 60 plus 90, 15 plus 60, delete 60 plus 90 is equivalent to 165. So this is equivalent to 165. But remember, we're not going to end there because we've been asked to calculate the theoretical volume in dm cubed. So at the end of the day, to convert to dm cubed, we must divide by 1,000. So if we divide by 1,000 there, we're actually going to get 0.165, 0.165 dm cubed. dm cubed, like that. So now 7.6 rates are, will the measured total volume of the gases at the completion of the reaction be higher or lower than the value calculated on question 7.5? Will the measured total of the gases at the completion of the reaction be higher or lower than the calculated? So it is actually going to be higher than. It's going to be higher than. It's going to be higher than. Then we move on to question 8, which is 8.1. It reads, consider the following acid-base reaction that occurs in an indicator there. Then we have our indicator plus H2O to give us this, and then an X. So define an acid according to the Lowry-Bronsted acid theory, right? So according to this, an acid is a proton donor. An acid is a proton donor. So it actually donates H plus ions. So it donates H plus ions. That's what an acid does. Then if you were asked in terms of a base is a proton acceptor. A base is a proton acceptor. Then 8.1.2 reads, is the indicator an acid or a base in the reaction, right? So given that one now, if you had to look at this, so this versus this and that, you'll discover that in this is an acid. You'll discover that this is an acid. In HI, the indicator is an acid, right? So why do we say it's an acid? It's because it donates a proton. So the reason behind is that it donates a proton. It donates a proton. Then, or an H plus ion, if you want to put it like that, an H plus ion, right? Write down the formula of X, right? So the formula of X is actually going to be a hydronium ion. The formula X is actually going to be in hydronium ion, which is your H3O plus. It's the hydronium ion. Then we move on to, so it's the same as this and that, and then this one is actually going to be H3O plus, like that, right? H3O plus. Then the indicator has the following colors in different solutions. So we are having your acid, yellow, the indicator, yellow, then neutral is green, then base is actually blue. Then it reads, what will the color of the indicator be when it is added to sodium hydroxide solution? So sodium hydroxide solution. So you need to know what sodium hydroxide is. So sodium hydroxide is a base. It's a strong base, to be specific. This is a strong base, same as potassium hydroxide, KOH, is also another strong base. So according to these indicators here, we're having an acid, so sodium hydroxide is not an acid. Is it neutral? No, but sodium hydroxide is a what? Is a base. So automatically choose from yellow, green, or blue. So our correct answer is going to be blue. Why is it blue? Because sodium hydroxide is a strong base. Then we move on to question 8.2. A school laboratory has 100 cubic centimeters of hydrochloric acid, which is your HCl solution, with a concentration of 0.9 mole per dm cubed available. So then we are asked the first question to define concentration in words. So this is the amount of solute. Amount of solute. Where, to be specifically, per liter of solution. Per liter of solution. So amount of solute per liter of solution. Then now the next question says, calculate the number of moles of hydrochloric acid present in 100 cubic centimeters of this solution. So if you were to look at this, you will see that the volume is given in cubic centimeters. This volume is given in cubic centimeters. So what do you do if you're given in cubic centimeters? You're supposed to convert it to dm cubed. So according to the formula, your formula there, C concentration of HCl is equivalent to number of moles. C is equivalent to N over V, number of moles over volume, right? So now what we're actually having there is 100. So we're supposed to convert that 100 to a dm cubed. So how do we do that? We divide by 1,000, right? So convert 100, so 100 divided by 1,000, then you'll get 0.1. So now it's now in dm cubed. So first part, you're supposed to convert there. Therefore, your concentration you're given is, according to this information, they're saying calculate the concentration. So we're having 0.9 moles per dm cubed. That's the concentration that we're actually having there. Therefore, I'm going to say the concentration is 0.9, then is equivalent to the N, the number of moles over the volume, which is 0.1. 0.1. So if you cross multiply your N there, you will actually get 0.09 moles. So that's how you actually calculate your number of moles according to the data that is actually given. In the next part, we are supposed to under 8.2.2, it reads, all of the 100 cubic centimeter hydrochloric acid solution is allowed to react with 3.5 grams of an unknown metal carbonate. So this M is the one that is unknown. So it's a metal carbonate according to the balance equation, right? So this is the balance equation that we're actually having there. Then here it says the hydrochloric acid solution is found to be in excess. So there is more of it. There is more of it. So if we're having more of it, then now the excess hydrochloric acid, HCl, is neutralized by 25 cubic centimeters of sodium hydroxide solution with a concentration of 0.8 mole per dm cubed. So it says the neutralization reaction of the excess HCl is shown below. So sodium hydroxide according to the equation there, we're actually going to have a salt and a water. So it shows basically it's a neutralization reaction. So now determine by calculation the symbol of the unknown metal M. So we're looking for the unknown symbol M, right? So, but what we're actually going to start with is start with the number of moles N of sodium hydroxide. Why do we have to go for sodium hydroxide? The concentration there. So N is equivalent to C the number of moles, right? So if you can look here, we're given the concentration, we're also given the what? The volume. So this is the concentration. So the volume of is 25, and then the concentration is 0.8 mole per dm cube. So we're actually going to start there. Therefore, this is equivalent to the concentration, which is given 0.8, then multiplied by the volume. Are we going to use 25? No, you got that right. So we're supposed to convert that 25 cubic centimeters to dm cubed by dividing it by 1,000. So if you divide 25 by 1,000, we're going to get 0.0225. Then we multiply for us to get the number of moles. So if we do our math there, we're actually going to get a value of 0.02 moles. So these are the number of moles that we're actually having, right? So now, if we are to check the number of moles in excess or for sodium hydroxide are actually going to be equivalent to the number of moles for HCl. So why is that so? If you look at the mole ratio here for sodium hydroxide and the one for HCl is 1:1. So the number of moles that are in excess for sodium hydroxide and for HCl are actually going to be what? To be the same. So now, how much of it reacted? So now let's look at the number of moles of HCl that actually reacted. So remember, so N of sodium hydroxide is going to be equivalent to the number of moles of what? Of HCl. The one that is actually going to what? To be in excess. These ones are in excess. They are equal. They are equal. So now let's look at the number of moles of HCl that are actually going to react. Number of mole of HCl that are actually going to react is equivalent to, so how many did we start with here? We started with 0.09, 0.09. There, we have it there. We calculated them. So 0.09, then how much of it are actually going to subtract 0.02. We subtract that one. Then if we say 0.09 minus 0.02, we're actually going to get a value of 0.07, 0.07 moles, right? So moles. So why are we subtracting there? 0.09 minus 0.02, because we needed to know how much of HCl reacted with the what? With the carbonates. How much of the HCl reacted with the carbonates. So having that information now, we can safely proceed to say the number of moles of the unknown carbonates, which is your MCO3, MCO3, CO3 is equivalent to half of what? 0.07. The ones that actually react. So where do we get this one from? So if you can check the equation there, it says the mole ratio is 1:2, like that. It's 1:2. So that's why we're actually going through that path there. So if we divide there, it means the number of moles here is actually going to be what? Half of 0.07. We're actually going to get 0.035 moles, right? So these are the moles that we're actually having. Let's just go back to refer to the question. It says, determine by calculation the symbol of unknown metal M. So we're looking for the symbol of unknown metal M. So for us to get the symbol of the unknown metal M, so it means at the end of the day, we need to know the molar mass of this one, right? So to calculate the number of moles, so for N, remember N, MCO3, according to the formula, is equivalent to M all over M. So the small letter M is the one that we're actually looking for, the mass there, right? So what we're actually, the molar mass is the one that we're looking for, right? So if we're to calculate this one, we're actually going to say M capital letter M is equivalent to M N. Like that. So if we were to create space there, let me erase here. Start all over. So if we were to make this capital letter M the subtotal formula, M is equivalent to, if we make M the subtotal formula is equivalent to M over N, like that. So now having that information, now we know M is equivalent to, therefore your M is equivalent to 3,5 over 0,035. So if you divide that one, the mass and the number of moles is actually going to get what? We're actually going to get, if we divide 3,5 divided by 0,35, we're actually going to get 3,5 divided by 0,035. We're actually going to get 100. So there we get 100. So having 100 there, so this is 100 grams per mole. This is what we're actually having. But take note of, it means everything should actually equate to 100. So the M and plus carbon has got a mass of 12. Then plus oxygen multiplied by 3 there. What are we actually going to get? 16 by 3, 16 multiplied by 3 is 48 plus 48 is equivalent to 100. Therefore, we make M the subtotal formula. Therefore, M is equivalent to how many? 40 grams per mole, right? So if we go to our data sheet, we'll find that the M there stands for what? For calcium, according to our periodic table. Then we move on to question number 9. Question 9 reads, a clean piece of copper Cu is placed in a solution of silver nitrate HgNO3. Then the balanced net ionic equation is Cu solid plus 2He to give us Cu. Look, that's the equation, right? Then it says define the term reduction in terms of electron transfer, right? So reduction is the gain of electrons. Gain of electrons. So how do we go about it? So oxidation, remember, we use the acronym RIC. IH there. RI. So oxidation is the loss of electrons, whilst the reduction is the gain of what? Of electrons. So in terms of electrons here, define reduction in terms of electron transfer. So reduction is the gain of electrons. Then we are asked, what type of reaction does copper Cu, which is a Cu, undergo in this equation, right? So if you can check that out, so copper undergoes oxidation. Choose from oxidation and or reduction, right? It undergoes oxidation. Then we're supposed to explain our answer by referring to the oxidation numbers, right? So if we can check the oxidation number of copper increases from 0. So here, if it's like this, according to our oxidation numbers, any neutral element has got an oxidation number of 0. So here we've got 0. Automatically here there is a positive. Then here there is a positive 2 plus. So here it means it started as 0, then ended up being what? 2 plus, right? So it means our oxidation number is actually increasing. So oxidation number of Cu increases. So the explanation is that the oxidation number of Cu, which is your copper, increases from 0 to 2 plus, or plus 2. So that's how it actually increases. So it started with an oxidation number of 0, now ended with an oxidation number of what? Of 2 plus there. That's how we know it underwent oxidation. Remember, when in terms of defining this in terms of oxidation numbers, right? So if you are to define this in terms of oxidation number, oxidation is an increase in the oxidation number. So oxidation in terms of oxidation numbers, oxidation number. So oxidation is the increase in oxidation hash, right? So reduction, oxidation number also what decreases. Oxidation also what decreases. Therefore, now we move on to the next part. The next part that actually reads, write down the formula or name of the spectator ions in this reaction, right? So spectator ion, they do not take part in the what? In the reaction. So if we were to check there, which one actually do not take part there, right? So if you check here, we started with what? Silver nitrate there. Silver, then the nitrate part is not even there on that equation, right? So it means they are the ones that are referred to as the spectator ions. They have got no effect on anything. So the answer is going to be NO3 negative. So spectator ions is NO3 negative. Those are the spectator ions that do not take part in the what in the reaction, right? So it says write down the reduction half reaction. So we need the reduction half reaction, right? So which was actually reduced here. So oxidation takes place here. You started with He plus, and then you ended up with He, which is neutral, right? So here it means you started with a value of +1. Then where did you go? You went to 0. So what happened there? It means there was actually what? Reduction. You started with an oxidation number of 1, +1, and then ended up with something that is neutral, 0. So that's a reduction. So now this is what we are asked to do, the reduction half cell. So we're actually going to write it. We started with an He plus, and then what did we do? So it means if we're having a plus, it means we're having an excess of what? Of electrons or of protons, right? We're having more protons than what? Than electrons, right? So if I'm to add an electron there, it means here, since I have got an excess of 1, if I add an electron, it's actually going to what? To balance out. So at the end of the day, I ended up having a G like that. So that's how we're actually going to write our reduction half reaction. Then we move on to 9.2. Says sulfur dioxide gas, SO2, is bubbled into an acidified solution of potassium permanganate as shown in the diagram below. So that's the gas that is being bubbled into potassium permanganate as shown in the diagram. It is observed that the solution turns from purple to colorless. From purple to colorless, it started from purple to colorless due to the reduction of what? MnO4 negative ions to Mn2 plus ions. During the reaction, SO2 is oxidized. So your sulfur dioxide is oxidized to sulfate ions SO42 negative. Determine the oxidation number of sulfur in SO42 negative, right? So generally what you're actually going to have there is okay. So what we're actually having here is SO42 negative, right? So if you look at this whole compound is not what is charged. It's charged. So if it is charged, it means the overall charge for this compound is actually going to be -2. But if you look at sulfur, the one that we don't know, we're actually going to put in what? A charge of what? Of X there, right? Of X. This one is X. Then for oxygen, we always know the oxidation number for oxygen is always going to be -2. Then the overall charge is actually going to be -2. So if we were to say your X, which is unknown, and then we add it to plus, then bracket -2, right? -2, then we're actually going to multiply by 4 because we are having how many oxygens? 4 oxygens. Should actually give us a -2 because the overall charge for this is actually what? A negative. So if we were to do our math there, it's going to be x minus 8 is equivalent to -2, right? So 8 is equivalent to a positive 6 like that. So it means the oxidation number, write down the oxidation half reaction. The oxidation number here is actually going to be a +6 like that. Then after that it says, please take note, you write it as a +6 with a +6, not just a 6. It should be +6. Then we move on to the next question that says 9.2.2 oxidation half reaction. So the oxidation half reaction is actually going to be, according to this one, it's actually going to be our sulfur SO2 plus H2O to H2O, then it's actually going to react and then give us SO2. If we react this, it will give us SO4, then 2 negative, then plus. If we were to balance the number with the number of hydrogens, how many nitrogens do we have on the right? 4. So it's going to be 4H plus, then plus 2 electrons. So that's how we're actually going to write this one out. So SO2 plus 2H2O to give us that then after that plus 4H plus 2 electrons, right? So these are there to balance the number of hydrogens on our left hand side there. Then question 9.2.3, last but not least, of course. Then it says, write down the balanced net ionic equation using the half reaction method. So let's clear this so that we can work it out. Let's clear this so that you can work it out. For what we are actually having here, we're actually going to divide this into 2 parts, right? So start with the oxidation half reaction. Oxidation, the half reaction for oxidation is actually going to be SO2, then plus 2H2O, plus 2H2O, and then it actually gives us SO42 negative plus 4H plus 2 electrons. Then now the second part, we must also write the reduction part. Reduction, then we balance it out after reduction. So your reduction part is actually going to be, you started with this MnO4, the NO4 ions, and then we are told it formulated what? Mn2 plus. So we're actually going to start with our MnO 4 negative, then plus hydrogens, I'll leave them for now, then plus 5 electrons so that we can balance them out. Then to give us, if we were to check there, it should actually give us Mn2 plus. Then if we're having our Mn2 plus, then plus the hydrogens plus H2O, right? So now if we're having H2O, originally at the top there, we're actually having how many hydrogens? 4 hydrogens. So we're supposed to multiply by 4 this year. We're actually going to have how many hydrogens? 4 H2O. So if we're having 4 H2O according to the table, 4 H2O, it means here we are supposed to have 8 hydrogens, then 5 electrons, like that. So now after that, we're supposed to work it out as the net ionic equation. So the next step is for us to identify the net ionic equation. So the net ionic equation is for us there to eliminate any spectator ions and all, right? So at the end of the day, we're actually going to have our, if we multiply by the number of electrons at the top there, we're actually going to say 5 SO2, the water plus 2 MnO plus 2 MnO4 negative. Take note, this number of electrons are multiplying the top part, and then these two number of electrons, they are multiply the reduction part. So if you multiply there, what you're actually going to get, then at the end of the day, you're actually going to have 216. And then H2O, then plus we're having 2H2O, 2H2O, then to give us the product there. So our product there is actually going to have what? Our sulfur, SO4. It's actually going to give us a sulfate there, which is our SO4. Then the SO4 is going to be 5 SO4, SO4, 2 negative, then plus how many nitrogens do we have there? 4 H plus, and then plus what is left? What is left is Mn plus 2 Mn, 2 Mn, 2 plus. So that's how we actually work out the net ionic equation.